and chemical bonding. This is a new chapter, chapter 7. This is material that will show up on our exam 3. There's also a lot more conceptual stuff in here, so if you've been real sick and tired, I'm sick and tired of all this algebra nonsense, there's not as much algebra in this chapter, so that might be nice for you. Light is a form of radiation. Specifically, it's a type of what we call electromagnetic radiation. It is not matter. Light does not take up space, and it doesn't have mass. So no mass, doesn't take up space, or doesn't occupy space. Because those are the two things that we need to be matter. Light is a form of energy. It travels through space in a vacuum at a constant speed, and it's this 3 × 10⁸ meters per second, which is super, super fast. Light has properties of both waves and particles, which we won't get into in a ton of depth in this class. Often called the wave-particle duality. It can behave like a wave, it can behave like a particle. So it's pretty interesting in that way. The wave part of it, if you think of a water drop falling and hitting the surface of some water, you can see the rippling waves that flow out from it. That's what sort of the thing we're talking about when we're thinking of waves. We're thinking of sound waves. We're thinking of some up and down repeating pattern in terms of energy or amplitude or something like that. Waves carry energy as they move through the water. So when those waves hit, if you think of being at the beach is really nice and peaceful and calm and quiet until the waves come and hit you. You get a couple of moments and then boom, you get smacked by a giant wave. We've all seen those funny videos of somebody doing an influencer photo shoot and then they get smashed in the back by a giant wave and they face plant in the sand, right? Funny stuff like that. So waves carry energy as they move through the water. Light also does that. There's some properties of waves. So we'll talk about some of the wave-like properties of light. Waves have wavelength. This is not like the height of the wave, this is the distance between waves. So wavelength is the distance between waves. I don't know if it's strictly speaking only the distance between the crests. So there's crests and troughs for waves. So here we're looking at like a mathematical representation of a perfect wave. So it has this repeating up and down pattern. And as the wave would actually be traveling, you can think of this whole up and down pattern just kind of moving from left to right. There's lots of good illustrations and like GIFs and things of waves moving. For visible light, the light that we can see, that our eyes interpret as colors and things, the wavelength determines the color. And wavelength is given this symbol, or we use this symbol lambda. So lambda is linked to the color for light. So if we look at short wavelength, the waves are close together. If we look at long wavelengths, the waves are more spaced out. Another property that you see, maybe you've seen mentioned here, coming up later, never mind. White light, as you may know, contains a spectrum of wavelengths. It's not just one wavelength, white light. It's all of the colors of the light, and famously can be separated by a prism to make a rainbow, all of the colors of light in a continuous spectrum. This can also happen like when light is going through windows. There's some other interesting effects where rainbows show up. Rainbows also show up. They diffract through raindrops, and that's why you see a rainbow. It's a similar thing to what's going on here, but with water drops instead of a prism. Another important note about the way that light works, the color that you see is the color that is reflected. Or the colors that are reflected. So plants, a lot of plants look green. The chlorophyll molecules, those are the things that give them power, that give them energy. Those chlorophyll molecules absorb blue and red wavelengths, and they reflect green light. So the color you see is the color that is reflected, not the color that is absorbed. So there are some tragic cases of people buying plants and giving them a green light to help them grow, to give them lots of energy so that they don't have to be out in the sunlight. Plants look green because they reflect green light, and so if you give them a green light, the plants can't get any energy from that green light and they will just die. So that's why those are tragic stories. Plants want a red light. So often, like if you've seen grow light setups, they'll either be LED now, or they'll be red lights. Traditionally, they would have been red lights, I think. White light also works. Okay, the other property that I referenced, it's finally here, frequency. So frequency is related to wavelength. Frequency has this symbol that looks like a V, but is actually the Greek letter nu. And so I usually write that with a little chunk out in front. Not a chunk, but a little line out in the front. That's how I usually write the letter nu to distinguish it from V. Frequency is the number of cycles or crests that pass through a stationary point in 1 second. And frequency has units of inverse seconds, which is 1/seconds, which is the same as hertz. So the number of anything per second is hertz. Frequency also has units of hertz. Wavelength and frequency are inversely related. So short wavelength corresponds with high frequency. If your waves are really close together and the waves are all traveling at the same speed, if they're really close together, you'll get a lot of waves through all at once. You could sort of think of this as like if you've got a convoy of like a bunch of people walking and they're all, just as tightly spaced as they can. You've got a real nice single file line of people walking and they're like walking through a checkpoint. The number of people that goes through that checkpoint is going to be high frequency. You get lots of people through. If everyone's individually in their own semi-truck and they're going the same speed as the people that are walking, now they have to go a whole semi-truck's length before the next person passes through that checkpoint. It's a really inefficient way of moving people through, if that's helpful at all. Let's also go back and look at this. So here we've got short wavelength and high frequency, so the waves are closely spaced together. If we think of those waves moving at the same speed, this top one and this bottom one, you'll get a lot more waves passing through in this top one, so that would be high frequency, lots of waves per second. In this bottom one, your waves are more spread out, so you're not going to be able to get as many waves passing through in the same amount of time. So that's the wave part of light, but there's also a particle part of light. So light can also be viewed as a stream of particles. It behaves like particles sometimes. We've got a little piece of vocabulary here, photon. A photon is our smallest unit of light. You can think of it as a packet of light energy, one light piece, sort of. And these photons, the amount of energy that they carry is proportional to inversely proportional to their wavelength, directly proportional to their frequency. Yes. So low wavelength equals high frequency corresponds with high energy. So lots of closely spaced waves. That's the short wavelength part. The waves are really closely spaced together. The crests, the tops of the waves are. Means a lot of waves traveling through the same point at the same amount of time, and that's a lot of energy. The analogy that I like to think of, I like to relate it to the beach, because that's, I think, where most of us think of when we think of waves. If you're at the beach and the waves are crashing, wave crashes, wave crashes, wave crashes, right? Real nice and slow, a normal day at the beach. It's relaxing, it's soothing, it's low energy, you can relax, you can chill out. If they're rapidly crashing, wave crash, wave crash, wave crash, like during a storm, that's not going to be quite as calming, soothing. That, to me, my brain thinks storm, something's going on. So high frequency of waves crashing at the beach, that's a lot of energy. It's not quite as calm and peaceful, a little bit more chaotic. So here's those relationships. You're welcome to just memorize them if you'd like to. And we've got this big graph, this big diagram of all of light, all of the electromagnetic spectrum. So it goes from radio waves, the same ones that you listen to the radio on, AM, FM, all the way up to gamma rays and everything in between. And our visible light spectrum is this tiny little bit in the middle. And the visible spectrum runs from about 400 nanometers to 700 nanometers for the wavelength. I'll talk about a couple of ways to remember the order of the visible light spectrum, because I think that's helpful. It's sometimes nice to know. What do we notice about the order of colors in the visible spectrum? What order are they in? Left to right or right to left, it doesn't matter. They're in the rainbow order. We've all seen a rainbow. We can probably all come up with the rainbow order of colors, even if you don't remember Roy G. Biv. The colors are in the order of the rainbow. So that's an important piece of like base knowledge for putting together, like, what's the frequency, what's the wavelength, and how do those relate to each other for different colors. They'll always be in either forward or backwards rainbow order for a pattern. The mnemonic device that I know for this, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Okay, so getting into our electromagnetic spectrum, we've got gamma rays and X-rays. These are the highest energy wavelengths. Gamma often is given the symbol gamma, the letter gamma. It looks kind of like a Y, but it's got some extra flair to it. Gamma rays will be making an appearance towards the end of the class, like the end of the semester. We'll see them again. This isn't the only time we see them. Gamma rays have the shortest wavelength, and they are also the most energetic. Gamma rays get produced by things like the sun and the stars, and certain unstable atomic nuclei, which is where we'll be seeing them again later in the future. Gamma rays are really bad for you in large amounts. Fortunately, our Earth has some shielding because of, I don't remember if it's magnetism or if it's the atmosphere or whatever, but a lot of the gamma rays get diverted around the Earth, so we aren't exposed to large doses of gamma rays, otherwise we would die. one of the issues with going to other planets, I think it is the atmosphere that protects us. Maybe it's the magnetosphere. It's one of those two. One of the issues, though, with going to other planets, like going to Mars or to the moon and trying to live there, is that they don't have the same level of gamma protection, if I'm remembering correctly. So you would have to constantly be wearing a suit that protects you from gamma rays, like an astronaut suit, or you would have to be in some sort of like heavy lead shielded or concrete shielded building. X-rays are the same ones you get at the dentist. Same ones at the dentist or the doctor's office if you break something or think you might have. X-rays are the next highest energy, so a little bit less energy than gamma rays, which means they have a little bit longer wavelength. The waves are spread out a little bit more. And X-rays are useful because they can pass through solid substances. Gamma rays are also useful. They're just a little bit more specifically used because they're higher energy. So X-rays will pass through your body. They won't pass through things like lead, so that heavy apron that your dentist hopefully puts on you when they do your X-rays. Hopefully we're getting our X-rays done once a year. That heavy vest thing, that's a lead apron to protect your body from getting that X-ray radiation dose. If you remember what it's like to go to the dentist and get your X-rays done, hopefully we've all had that experience. The person adjusts the little camera thing, and then they walk out of the room and they press the button and it makes the little tone, and then they walk back in and they adjust it and they walk back out and they press the little button and it makes the tone. The reason that they're doing that walking in and out bit is because they would also be experiencing those low doses of X-rays, and since they're doing that many times a day, that drastically increases the amount of X-ray radiation they'd be exposed to. So that's why they step out, to reduce their rate of cancer. There's a lot of fun stuff, I think it's fun, that I'm going to be talking about during this chapter, and some of the other chapters as well, but especially this chapter, because I think it's fun and interesting, but it's not going to show up on exams. It's just kind of like, now you know more about the world. Okay, moving on in our spectrum, we've got ultraviolet or UV light. This is the sunburn component of light. This is what sunglasses protect your eyes from as well. So usually it's separated into UVA, UVB, UVC. And sunglasses typically have a UVA and a UVB rating, where they protect you from both. UVC is used for like sterilizing stuff. So the little cabinet that our lab goggles live in has a light in it that uses UVC light to sterilize the lab goggles, if we use it. These are less energetic than X-rays. You're exposed to them anytime you go outside, and even a little bit probably when you're inside. But so they're less energetic than X-rays. They're still damaging to biological molecules. If you're outside for too long, you're more than likely to get a sunburn, depending on what level of protection your body has. So UV light causes sunburn. Visible light, this is the good light, this is the pretty light, the stuff that we can see, this is all of the colors. So this is what makes life pretty. The different wavelengths of light cause molecules in our eyes to rearrange and gives us vision. Your eyes have rods and cones in them, and cones see color because they're pointy. That's not actually why they see color, but that's what I've remembered since freshman biology in high school. Cones see color because they're pointy. That's stuck for some reason. So visible light, good stuff, not going to damage your eyes. There's also even less energy than visible light. We've got infrared or IR light. So a lot of like TV remotes and stuff, stereo remotes use infrared light to communicate between your remote and the TV. You can't see it usually. There's maybe a little bit of a faint red glow to it. The Wii, the Nintendo Wii, the remote also uses infrared light. So the little sensor bar thing has some infrared lights in it, and then there's a camera in the Wii remote that picks up the infrared light. So if your sensor ever dies, you can actually also use like 2 little tea candles. That'll also work for using your Wii. But then you're burning candles. Infrared light is also emitted by hot objects, and anything that's warm, any warm object, including human bodies, emits infrared radiation. And as this last bit says, often used for aversion of night vision. Or heat mapping. I think we've got a slide that's got some heat mapping or heat imaging. One of the issues with this type of night vision technology is that usually you have to have infrared light on your helmet as well. So anything that can see infrared can also see you because you've got a big, bright flashlight basically on your head. Infrared light, not bad for you. Our bodies are emitting it. Not going to burn you or give you sunburns. All right, here's this photograph that I stumbled upon that I think is super cool. So we've got an infrared photograph over here on the right. We've got an overlay of the space shuttle, just the picture of it on the left, and then a heat mapped image on the right. So this sort of visible light, this rainbow sort of color thing that we're seeing here, this is mapping the infrared light, the temperature, to visible light so that we can make sense of it. So the red areas are the warmest, the blue areas are cooler. And this is a shuttle orbiter Columbia. This was returning to Earth on March 30th, 1982. So this is the shuttle in this picture on the right that says United States on the right. The picture was taken by this plane on the left. So there's a plane, the Kuiper Airborne Observatory was flying around and took a picture of the shuttle as it was coming back in from orbit, which I think is just crazy that they've got a plane taking pictures of other planes. For a little bit of tragedy, read up on what happened to the shuttle orbiter Columbia. That was an unexpected twist when I was looking into it. Further down, energy. So we had visible light, then we had infrared light. Now we're on to microwaves. Microwaves are confusingly used for radar and not confusingly, very straightforwardly, used for microwave ovens. So the microwave that you heat up food at home uses microwave radiation. So there are certain wavelengths that are efficiently absorbed by water. Your microwave is tuned to heat up water. So you can heat substances that contain water. That's how microwaves work. They're using microwave radiation. They're sending it through your oven to heat up the water molecules that are in your food. So if you heat up food that doesn't have a lot of water in it in your microwave, it's going to take a lot of time for it to heat up. Or if it's got a really high heat capacity like a potato, if it's got a lot of water in it, likely to absorb a lot of that energy and heat up and become really hot. And then we've got radio waves, which I assume are also used for radar and are used to transmit radio signals and cell phones and TV and some other forms of communication. The reason that I say that it's confusing that microwaves are used for radar is radar means I believe it's radio detection and ranging. You don't need to know this. This is just, I'm explaining why I was confused. This is one of many acronyms. Like SCUBA is also an acronym. So radio detection and ranging, there's also other forms. There's light detection and ranging, LIDAR. Sonar, I think, is a similar thing. I don't remember what the N stands for, but it's similar sort of ideas. That's why I was confused about those being used for radar. All right, here's where we're going to, I'll tell you about my little hack. Actually, let's go back and I'll tell you about my little hack for remembering the order of light. We'll do it here. So the colors are in rainbow order. Squish. The colors are in rainbow order. Next to visible light, we have infrared light on one side and ultraviolet light on the other side. So we've got infrared and ultraviolet. What do we notice about those two words relating to visible light? There's a word within a word. There's a color in each of these, infrared and ultraviolet. Infrared is next to what color? It's next to red. Ultraviolet is next to what color? Any brave souls? Violet. It's right next to violet. Thank you. Somebody was thinking it somewhere. So infrared next to red, ultraviolet next to violet. Which one of those two causes damage to your body? Ultraviolet. Ultraviolet burns you. UV gives you sunburns. Hopefully we know that. Infrared does not give you sunburns. UV gives you sunburns. That means that it's high energy. Because it's right next to violet and the colors are in color order, violet is our highest energy light. So violet is our highest energy. And red is lowest. I'm going to shorten energy to E. So red is the lowest energy. And it scales, it's in order. So violets are highest energy. Next highest energy would be indigo. Next highest energy would be blue. Next highest energy would be green. Then yellow, then orange, and then finally our lowest energy, red. Red, the lowest energy, is also part of the reason I've been told that a lot of laser pointers are red. It's also because we can see red really well. If you use a violet laser pointer, they're much higher energy. You're more likely to damage somebody's eye if you shoot it at their eye. And we also can't see violet quite as well. More fun, not related stuff to the class. So that's how you can remember the energy order. And you might also be able to remember that energy and frequency are related. There's a way that we can remember the wavelength order. Track and field has different loops that people run on, right? If you've watched the Olympics, if you've watched any of the events, they run in their own little track for the first lap at least, and then they'll all maybe settle into the middle ones. On track, say we're running one lap, and I give you the option. We're going to start at the starting line, we're going to end at the finish line, which is also the starting line. We're going to run one lap. You can run on the outside track, you can run on the inside track. Those are different length tracks. Which one is shorter? The inner track is shorter, right? So if we're thinking of the end of a track, right? It's got that half circle loop. The outside is the longest. And as you get progressively closer to the inside, it gets shorter and shorter. So the outside is the longest. Also, if we took this rainbow and we stretched it out so that all the lines were straight, right, we would see that the red is the longest, then orange, and so on, down till we get to violet. The reason that I mention this is that red is conveniently the longest wavelength. And violet, or purple, or indigo, is the shortest wavelength. So if you remember the shape of a rainbow and that the outside track is the longest, you can put together the order of the wavelengths of light. So those are two tools that I think are helpful for remembering information about the visible light spectrum. Any questions about light before we do the exercises? All right, cool. I'm having a great time. Hopefully you're having fun too. All right, let's see what we remember from 10 seconds ago. Arrange the colors of visible light, green, red, and blue, just green, red, and blue, in order of increasing, so smallest to largest, wavelength, frequency, and energy. I'll give you a couple minutes. Feel free to discuss or fight with your neighbor. All right, we want to arrange green, red, and blue in order of increasing wavelength, frequency, and energy per photon. Which of these three, green, red, and blue, is our shortest wavelength? Blue is our shortest wavelength. What's next? Green or red? Yeah, we've got green next, and then finally we've got red. And we'll draw in some less than signs. So we've got shortest on the left, longest on the right. So we could think of our rainbow and the outside path is the red, so that's going to be the longest, and it works its way all the way down to blue. For frequency, what is our shortest frequency? If you're blind guessing, you've got a 33% chance. We got a guess for blue. It's not blue. Thank you for guessing. It's the opposite order. So frequency is opposite of wavelength. So our lowest frequency is red. Any guesses on what comes after red? Yeah, green. And then what happens, or what comes after green? It is blue. So red is our lowest frequency. Blue is our highest frequency. And then how about energy per photon? Which of our colors of light for visible light has the highest energy? Or lowest energy, because we've been doing lowest. What has the lowest energy for visible light? Red. So red is our lowest energy per photon. What's got more energy than red? Green's next. And last but not least, blue. Blue is our highest energy because it's closest to UV. Weird S. So for the wavelength one, we can think of that rainbow shape. For energy per photon, you might think of UV burns, not buns, UV burns, not burrs. One of these days I'm going to figure out how to write correctly. UV burns, that means that it's high energy. Violet is next to it. So highest energy for visible light. And then the order decreases from there, so all the way down to red. Any questions about wavelength, frequency, energy per photon? Let's say I ask you a superlative question, superlatives being things that end in est, like most likely to succeed, most likely to make $1 million, right? Superlatives from like yearbook in high school. Let's say I ask you for the mostest of any of the colors in the visible spectrum, the one that's the most anything, the most frequency, most wavelength, most energy per photon. Which of these colors should you never pick? Green. Why should you never pick green? It's in the middle, right? Green is in the middle. If red is an option and blue is an option, you've got orange, yellow, green. You should never pick orange, yellow, or green because they're not on either end. You should only pick one of the two outermost ones. Does that make sense? I say this because it drives me nuts that I ask a question that's a superlative question on the exam and people will tell me that the answer is like yellow. They'll choose yellow. And you have a 50-50 if you don't pick any of the middle colors. Never pick the middle colors. Don't pick the middle color. It'll never be the middle color. It's always going to be one of the outside colors. If it's a most question or a least question. All right, moving on sort of from colors. We've talked about atoms a little bit, how they've got a nucleus, how they've got electrons. The nucleus has protons and neutrons in it. We're going to do a really tiny amount of science history. It's very Eurocentric. So the Bohr model is the first one that we'll talk about. This is kind of an older model. You may know that neon signs light up. There's lots of different colors for neon signs. The way that neon signs work is there's neon atoms in there. Neon's a gas, and also conveniently, it's a noble gas. That's actually part of the reason why they use neon gas is because it's noble gas. So if your neon sign breaks, it doesn't explode. Like if you used something like lithium or helium or sodium and you made that a gas, those might explode. So there's neon atoms in there, and they pump a bunch of electrical energy into them. And some of that electrical energy gets picked up, the atoms get excited, and then they release that energy out into the world as color. So that's why neon signs work. That's why a lot of lamps work. Other elements can also do this. So a mercury lamp, if you take mercury and you give it enough energy, that color will be blue. If you take hydrogen and you give it enough energy, the right amount of energy, that color will appear pink. The light that's emitted by hydrogen contains specific and distinct wavelengths, wavelengths being linked to colors, so specific colors that are specific to hydrogen. What we're looking at is an emission spectrum. It's got bands on it. Anyone spot U2? Maroon 5? Wrong kind of bands. So we've got this red strip of light, right? That's one wavelength. We've got this sort of cyan strip of light. We've got sort of an indigo strip of light, and then more of a violet strip of light moving from right to left. I'll point these wavelengths out. Hydrogen will always emit. If If you give it energy, it'll emit those wavelengths, and there's some other ones probably that would show up further off to the left. But in visible light, those are the ones we see. Anywhere that you see black, color is not being emitted. So black equals no color emitted by hydrogen in this case. So we've got here comparing our hydrogen emission spectrum to some other spectrums. So hydrogen on top, that's the one that we saw on the previous slide. Helium also has an emission spectrum. What do we notice about hydrogen versus helium for their emission spectra? Anything that's different? There's more wavelengths. We've got more lines, and they're also in different positions. It's like if we take a look at this red line on our hydrogen emission, it's a little bit different from our helium emission. And these lines over here are also kind of not quite lined up, which could be an issue with just like the images that I pulled for this. And then there's nothing, at least on this version of the helium emission spectrum. Maybe it's just too dark, but there's nothing here to line up with this hydrogen emission. So the spacing is a little bit different. There's also more lines. And if we look at iron, iron has lots of lines, tons of lines compared to helium and hydrogen. And then in comparison, we've got our white light spectrum. So this is what you'd get if you took a prism, passed a white light through it, and separated all the wavelengths out. You get a continuous stream of all the different colors. And no matter how much you zoomed out, no matter how much you zoomed into this white light spectrum, it would always be continuous. There would always be colors of light in there. Obviously, for our iron, helium, and hydrogen spectra, there are just spots where there's no color. So one of the things that scientists have thought about in the past was why? Why do we only get those specific wavelengths for hydrogen? Why do we only get those specific wavelengths for helium and for iron and for neon, which is not on here? Why do they only emit specific wavelengths? And Niels Bohr came up with a model that explains this. So this is the Bohr model of the atom. We've got in the center a nucleus. The nucleus is where all of our protons and our neutrons are, our massive particles, our big particles, the things that go into our mass number. So our nucleus has our protons and our neutrons in it, and then our orbits are where our electrons live. So this is sort of like if we think of a solar system, if you think of like what we would think of as a top-down view of a solar system, right? The nucleus in the center would be our sun. This n equals 1, 2, 3, 4. Those would be where the planets orbit. So the electrons in the Bohr model spin around on these tracks. They just run around in circles on these tracks. So electrons orbit the nucleus on the orbit tracks. The orbit tracks are assigned values of starting from 1 and increasing. So numbered from n equals 1 and counting up. Some features of the Bohr model of those orbits. is that those are fixed tracks, and they have an amount of energy for those tracks. So the n equals 1 track is always exactly at that same distance from the nucleus. The n equals 2 track is outside of it. The n equals 3 track is outside of that. Orbits are fixed, and electrons can only be on those tracks. I'm calling them orbit tracks. So it's impossible to have an electron between those tracks. It always is on 1, 2, 3, 4, and so on. It's not allowed to be in between. They can move between the tracks. So you can jump from n equals 1 to n equals 2, or be in n equals 3 or n equals 4, but they have to be in those tracks. And the orbits are specified by n. N is what we call a quantum number. Quantum being related to quantized, like a fixed amount. So Bohr's explanation for why light is emitted with those specific amounts of energy has to do with this model. So when an electron is spinning around on this n equals 1 track, it can receive energy, either by electricity or by another form of light or energy, and it might jump up from n equals 1 to n equals 2. So an electron absorbs energy and jumps to n equals 2, for example. It gets excited. That's the actual, we actually call it excited. So the electron gets excited, it jumps up. So jumping up some n number, like n equals 1 to n equals 2. But you can't stay excited forever, right? We can't always be high energy. At some point, we have to go low energy mode. Electrons are the same way. So after a long day of excitement, the electron relaxes, drops to a lower energy n. But that energy has to go somewhere. So for us, we go out and we work a day, right? All of our energy is expended kind of doing our work, doing our learning, doing our playing, whatever we're doing. Electrons are not that complicated. They get energy, they jump up in orbit. To drop down in orbit, they can't just like do some sort of fun task. They can't play a game of softball in their adult softball league. They have to release energy some other way. So they relax down, and the way that they do that is they emit light. So dropping from the n equals 2 to the n equals 1, some amount of light is emitted that has a specific amount of energy. And so the reason that this is interesting, and the reason that this explains the emission spectrum, is since these tracks are fixed distances from each other, the energy difference between these tracks is also fixed. So anytime that an electron is dropping from n equals 2 to n equals 1, the photon of light that it releases will always be the same distance, or the same energy, because it's traveling the same distance. So energy from an orbit transition is always the same because the distances are fixed. Distances or differences are fixed. AKA always the same. So this red line, red being low energy, that's going to be the lowest energy transition. That might correspond maybe to this n equals 2 to the n equals 1. So an electron's on this n equals 1 orbit. It absorbs some energy. It jumps up to this n equals 2 orbit. After a while, through some process, it releases a photon of light in order to drop back down from the n equals 2 to the n equals 1. That distance in energy maybe corresponds to that red light. This cyan light, this light blue light, might correspond, since this is higher energy, that might be an electron dropping from n equals 3 to n equals 1. This is a further distance than 2 to 1, right? 3 to 1 is longer than 2 to 1, we can see that. And so that's going to involve more energy. The further that jump, the more energy is lost, the more energy that must be put out by the photon. And dropping from n equals 4 to n equals 1 would be even more energy. Questions or confusions about any of that? All right, last slide on the Bohr model. So the reason that the Bohr model is really cool is because it works. It does actually predict the lines of the hydrogen emission spectrum. So what we were talking about those electrons jumping between those different orbit tracks, that actually works, and you can predict the wavelength of light by each of those transitions. Like you can calculate the energy of the light and figure out the color of the light that's emitted. It only works for hydrogen. So it works for one element, it works for hydrogen. It does not work for any of the other elements. But it's exciting because it works for at least one thing. Later on in our history, the Bohr model gets replaced by a much more sophisticated model, the quantum mechanical model. So we will be learning a little bit about quantum mechanics. The tiniest little bit of quantum mechanics. However, don't let all of the Bohr model stuff go out of your head. We will still be reusing and recycling some of those concepts when we're talking about quantum mechanical model of the atom. Questions? Okay, then we'll pause there for our break. So we're going to jump into quantum mechanics now, and it is reusing some of the same ideas that we learned in the Bohr model. The applications aren't exactly the same. As I just mentioned a second ago, this is kind of like learning a new game. A lot of chemistry is kind of like learning that one game that your friend who's really into board games really likes, but it takes 4 hours to set up, and then you have to play for 10 hours. That's sort of what chemistry is. So there's an extra dose, I feel like, of that with quantum mechanics. We're going to learn some rules. We're going to learn some terms. And you're not going to understand them necessarily all the way. But hopefully we can at least memorize them and learn how to play the game at least well enough. Again, this is a relatively simple level of quantum mechanics, because if you really want to get into quantum mechanics, you have to invoke physics, or sorry, not physics, calculus, and I don't want to do that. If you look at the Wikipedia page for quantum mechanics, it looks like it's written in a foreign language, even though it's written in English, and a lot of the physics stuff is generally universal. Okay, so the quantum mechanical model replaced the Bohr model in the early 20th century, so the 1900s. This is revolutionary because electrons don't actually behave like particles flying through space. You might be asking yourself, well, if they don't behave like particles flying through space, how do they behave? It's complicated. But the idea is they're not actually traveling around in little orbits, nice and neat orbits like we saw with the Bohr model. They're much more complicated. And so we're replacing Bohr orbits. Friendship with Bohr orbits is over. Quantum mechanical orbitals are our new best friend. That's referencing a meme. Okay, Bohr orbits are now orbitals. So instead of orbit, we added a couple letters, and it's an orbital. But it's representing similar ideas. So we can still think of orbitals sort of as being a track. They're not a track, but they're a similar sort of idea. Our orbitals are actually probability maps. We'll be showing you, or I'll be showing you some shapes. Those are how we represent the orbitals. But it's a statistics thing. It's where we're most likely to see the electron. The electron will be there most of the time. I've described this other times. Orbitals are kind of like if you know your friend, you know what their schedule is, you know what sort of things they like to do when they wake up, when they go to bed, your besties. You can predict, probably with pretty decent certainty a lot of the time, where they're likely to be. Oh, it's Monday at 12:30 p.m. They're probably at work. They're over in this area. That's a little bit like with orbitals. We can predict where the electron is. Oh, the electron's probably in here. It might be, though, that your friend has a dentist appointment. They're at the dentist, or they're at the doctor, or they decided to go somewhere extra long on their lunch break. They've got that leisure. Right? They're not always going to be there. We're just predicting. We're saying most of the time it's likely to be there. And then here's a couple of fun quotes from Niels Bohr, who came up with the Bohr model. Anyone who is not shocked by quantum mechanics has not understood it. Erwin Schrödinger, that guy that's famous for having that cat. I don't like it, and I'm sorry I ever had anything to do with it. And then Richard Feynman, who we saw quoted in that Yale video that I played for us a little bit. I think I can safely say that nobody understands quantum theory. Right? So these are three kind of intellectual giants specifically in this area of work, in this area of academics, with some really fun quotes about what we're about to be learning. So don't feel bad if you don't understand it, at least not intuitively, but hopefully we can learn how to play the game. The math and calculations, as I mentioned earlier, are beyond the course. Okay, so moving from orbits to orbitals, our orbits in the model are those circular paths. They're very predictable. Our orbitals, again, very unpredictable. It's a probability map shape. Orbitals have shapes to them. They have a specific shape, and that's where we're likely to find our electron. They're very unpredictable, though. Our orbitals are specified with a number and a letter. So we're reusing the lowercase letter n, which was our quantum number in quantum mechanics. It's now our principal quantum number. So we can think of n is layers of electron shells. So we've got our n equals 1, that's our inside shell. Our n equals 2 is our next shell. Our n equals 3 is our next shell. Our n equals 4 is our next shell. So we've got these different layers, kind of like our orbits, or 1 was the smallest, 2 is bigger, 3 is bigger, 4 is bigger. It's the same sort of an idea. We're still building out bigger levels, and the energy also increases. So there's some things that carry over from the Bohr model. The letter part indicates the subshell. Subshell is a specific type of shape that's defined by some really intense math. So the orbitals are specific shapes. A subshell contains orbitals. It has a bunch of different shapes within it. It's a specific type of shape. Our options are S, P, D, F for subshell. Quantum number will often be shortened to Qn. We don't have to do that as much in this class because we're not going into all of them. We're not going super in-depth into a lot of it. Okay, so with our pairing of principal quantum number and subshell, S, P, D, or F, our first orbital is the 1s orbital. 1s is the lowest energy. Out of all of the orbitals, all of the number and letter combinations, 1s is the lowest energy. And because we exist in three-dimensional space, orbitals also exist in three-dimensional space. So this, on the picture, on the screen, looks like a circle. It's supposed to be a sphere, so think of it as a round sphere. All of our s orbitals are spheres. S equals sphere. How nice. S for sphere. So our probability map for our 1s electrons is they're most likely going to be found in something that looks like a sphere, and it'll have a specific size to it. Our 1s is going to be our smallest, but it's going to be in some sort of spherical distribution. At room temperature, for an undisturbed, regular hydrogen atom, the one electron is going to be in the 1s orbital. So hydrogen has one electron. It's normally in the 1s orbital. This is its lowest energy state, its normal state, and we call that the ground state. The ground state is the lowest energy state, so nothing's excited. Everything is as relaxed as it can possibly be. My ground state is in my bed at home. That's my lowest energy state. I don't spend enough time in my ground state. We will be learning ground state for electron configurations, where the electrons are. If you are out of your ground state, that's caused by the absorption of energy for electrons. That's an excited state. Atoms always return to their ground state, just like we hopefully always return to our bed for the rest of our lives. And part of the reason that we're learning the ground state is because there is exactly one ground state, but there are very many possible excited states. Hydrogen has the fewest excited states because it only has one electron. The more electrons that you have, the more possible configurations of where you can have different amounts of excited electrons. So we'll just be learning the ground states. All right, so we talked about our n equals 1 principal shell and the s subshell that's within it. N equals 1 only has 1s. So it only has the one subshell. It only has s. And then we move up to n equals 2. So n equals 2 is next. And it also has an s subshell, which is also a spherical shape. Because the number has gone up, the 2s is bigger. It also has a p subshell, which we're not going to look at on this slide, but we'll see it soon. Our 1s orbital, if we represent it as the small sphere, is smaller than our 2s orbital. Our 2s orbital would be slightly bigger, but it's the same shape. It's still a spherical shape. Our 3s, since we've jumped the number up again, the size of our sphere also increases. It's a bigger sphere. We also have our 2p subshell. Our 2p subshell contains 3 orbitals, whereas our s only has 1. Our s only has that one specific sphere shape. Our p subshell has 3 different shapes. So there are these dumbbell shapes, p for dumbbell, S for sphere, P for dumbbell. Yes, unfortunately, S is the only one that it works nicely for. So P for dumbbell, we've got one that's along the z-axis. So it's got a long lobe that sticks out towards positive z, that's up, negative z, down. Our PX is along the x-axis, which is sometimes running forward and backwards, or sometimes running left and right, depending on which version you use. And then PY, which is along the y-axis. You don't need to remember the specific names, the PZ, PX, PY. I just show them to you because I think they're interesting and you might think they're interesting too. The key takeaway is that they have this dumbbell shape and there are 3 of them. They also, because of being along the different axes, they don't overlap with each other. So all the way here in the middle, where it looks like they might overlap, there's actually nothing there, because that's where the nucleus is, and you'll never find the electrons in the nucleus. Okay, so P is dumbbell. There's 3 dumbbells. And our P subshell shows up for the first time in our n equals 2. So 2P is our first version of the P subshell. Knowing what we saw on the previous slide with our S subshell, our 1s was small, our 2s was bigger, our 3s was bigger than that. Any guesses, if this is the size of our 2p's, how would our 3p subshell compare? Would they be bigger or would they be smaller? Yeah, we've got a guess for hand gesture of increasing size. Yes, they're bigger. So as n equals goes up, the size of the individual orbitals also goes up. So each of these specific shapes is an orbital. The subshell determines the set of shapes that we have, or the type of shape that we have. Up to a certain point, up to n equals 4, the number of subshells is equal to the principal quantum number. So those 1, 2, 3, 4, etc. The number of subshells that we have also goes up. So in n equals 1, we just have the S subshell. So 1s. And then we have to move up to our next highest energy shell, which is n equals 2, or principal quantum number 2. We can have 2s and 2p. And those are the only 2 subshells, the only 2 types of shapes that we have. Then we can move up to n equals 3. And we can have 3s, 3p, and 3d. And when we get up to 4, we have 4s, 4p, 4d, and even 4f. So the principal quantum number equals the number of subshells, the number of different letters that we have access to, up to 4. So moving past our n equals 2 to our n equals 3, we've got 3 subshells, because n equals 3. n equals 3, so 3 subshells, aka letters, S, P, and D. Our s orbitals, our 3s orbital is also a sphere. Our 3p orbitals are also dumbbells. And then our d subshell contains 5 d orbitals. So s for a number of orbitals. How many individual shapes did we have for s? Just one, right? We just had that one sphere shape. S, we have one orbital, one shape. The type of shape is sphere, and that one shape is just the one sphere. For P, that's our dumbbell shape. How many dumbbells do we have? We had one along the Z, one along the X, one along the Y. So we had 3. Our D subshell has a different shape and a different number of those different configurations of the shape, and we have 5 orbitals. Would anyone like to venture a guess how many orbitals F has? Some hesitant guessers saying 7, and it is 7. Would have been diabolic if it was like 8, right? But no, it's 1, 3, 5, and 7. So the number of orbitals increases as you go up, and it's only odd numbers. And these are the d orbitals. So we've got 5 of them. Up in the top left, we've got our d, y, z. Again, you don't need to know the subscript names. You don't even need to know these shapes necessarily. You just need to know the number of them. I show you the shapes because that can sometimes help with learning. I explain the sub-labels because I think it's interesting. So the d, y, z, it's double dumbbell, so d for double, maybe. That might work. Double dumbbells. The y, z, these lobes are in the plane that's formed by y and z. So if y and z is like the board, right? The z would be the up, down, the y would be the left, right. They're off in diagonals. So they're not touching the axes, they're between the axes. And then for dxz, it's now basically the board. So if I do an X shape with my body, my hands and my feet are each one of the lobes. It's just rotated 90 degrees, so now it's between the x and z axes. If we go to dxy, that's what I do when I go to sleep, laying down, right? Do starfish? I don't actually starfish. But it's between the x and the y axes. Then we've got the dx squared minus y squared. This is along the x and the y axes. And then we've got the dz squared, which is the weird one, the odd child. So the dz squared one, we've got one dumbbell that's up along the z-axis, and then our other dumbbell, for some reason, turned into a donut or a torus. So that one doesn't really fit with the double dumbbell. But generally, double dumbbell is a nice way to remember these. Again, you don't need to know those shapes specifically, but you should know the number of them. Other things that we can do with this information, right? So we've learned letters and numbers. Numbers being 1, 2, 3, 4, etc. Letters being S, P, D, F. We can have our 1S, 2S, 2P, 3S, 3P, 3D, and so on and so forth for 4 as well. Those are where the electrons live when they're in their ground state. And so we can represent or write out where those electrons are with an electron configuration. An electron configuration shows where the electrons are. So what principal quantum number and subshell, and also how many. So how many electrons are in that 1s, that 2s, that 2p, those shapes. For a ground state hydrogen atom, hydrogen has 1 electron. Our lowest energy orbital, our lowest energy shape, is our 1s orbital. And so that 1 electron goes into our lowest energy orbital, which is 1s. So 1s here representing our orbital, the superscripted 1, the raised 1, representing the number of electrons that's in 1s. Does anyone have questions about anything we've covered so far? All right, more about our electron configuration game. There's another way that we can represent them. We can also do an orbital diagram. Orbital diagram is similar. It's a visual version of an electron configuration. This tells us basically the same information, but provides a tiny bit more information. So boxes or underlines represent orbitals. And we're not going to do sublabels for our orbitals. The like px, py, pz, we're just going to label it p. So for hydrogen, our ground state hydrogen atom, in our 1s orbital, our one spherical shape, our smallest shape sphere, we have an electron that we represent with an up arrow. The up/down arrows represent electrons. One arrow up equals one up photon. Sorry, equals 1 electron. One arrow down also equals 1 electron. The up and down part of it is referring to the spin of the electron, which makes so much sense, right? Formally, electrons have spin, air quotes, and it's either up or down spin. That's actually what they call them, up or down spin. So that's what the up and down arrows are representing here. That's why we draw them as arrows up or down. So here's what I was saying, that direction of the arrows represents the electron spin. It's either up or it's down. And we've got our first of 2 rules for electron configurations. First of 2 named rules, at least. The Pauli exclusion principle. This would be a good one to memorize. So this is one of the rules of the game. Let me do a better job drawing this box. The Pauli exclusion principle states that orbitals, boxes or underlines, can hold no more than 2 electrons, so a maximum of 2 electrons per orbital, and they have to have opposing spins. So if we've got our 1s orbital, I often draw it in as just an underline because I don't want to draw the rest of the box. We can have a maximum of 2 electrons, so 2 arrows. And they can be pointing up or down. typically, I will always draw in up arrows first and then down arrows afterwards. I don't think that formally there's a reason that we can't do down arrows first, then up arrows. So just convention. And I'll usually draw them as half arrows, or one-headed, or one-winged. Anyway, half arrows. So for example, we could have up and down. This is allowed. This is good if we have 2 electrons. What we cannot have is 2 up arrows. That is not allowed. That is illegal. We also cannot have 2 down arrows. Also illegal. And we definitely cannot have 3 arrows. This is super illegal. So those are 3 things that we cannot do, or 3 configurations that would be not allowed, and 1 that is allowed. So we can have up and down. You could choose to draw the down arrow on the left side and the up arrow on the right side. It doesn't matter really to me. It might bother me, but I don't think that there's a reason we can't do that. So this is what the Pauli exclusion principle is saying. They have to be opposite spin, maximum 2 electrons per orbital. All right, I will show you now some electron configurations and orbital diagrams for helium and lithium. So starting with helium, helium symbol is He. How many electrons does helium have? Helium has the atomic number 2. That's that 2 in the top or in the top right. That 2 means that it has 2 protons. That also means that it normally has 2 electrons. So helium has 2 electrons. The first place that we put our electrons is in the lowest energy spot possible. Our lowest energy spot is what combination of number and letter? 1 is our lowest number, and then S. So 1s. In our 1s, we have one shape. We've got one sphere. How many electrons can we put into that one sphere? That one orbital? How many electrons can we put into one orbital? Up to 2. We can put 2 electrons into an orbital. So we can put both of our electrons in to the 1s. So this is 1s2. That would be our complete electron configuration. So our electron configuration is 1s2. Our orbital diagram, this is the picture version. Oftentimes we'll do an electron configuration first and then build an orbital diagram after that. Our orbital diagram, we're going to have one underline labeled 1s. And according to our electron configuration, 1s is first, and we've got 2 electrons in it. So we need to put 2 arrows into this underline or box. If you really want to draw the boxes, you're welcome to draw the boxes. It doesn't matter to me. We can put the first one in with up spin. What spin can we give the second one? Something you might tell your dog. Down. So up and down are our 2 options, or our 2 electrons. So that would be our complete orbital diagram for helium. Any questions about putting together the electron configuration or orbital diagram? The next element on the periodic table is lithium. We're going to do electron configuration and orbital diagram for lithium. Lithium has how many electrons? 3. Lithium has 3. Its atomic number is 3, so it also has 3 electrons. So for the electron configuration, our first orbital, our first number and letter pair is 1s. How many of our electrons can we put into 1s? 2. We can put 2 of our electrons into 1s, which means that we've got 1 electron left over. We don't have any more subshells. We don't have any more letters in n equals 1. So we have to jump up to our n equals 2. And in n equals 2, we have s and p, and s comes first. So we have 2s, and we can put our last electron there. So our electron configuration for lithium is 1s2, 2s1. And then we can use our electron configuration to build an orbital diagram. So our orbital diagram, we're going to have a box for our 1s. We'll have a box for our 2s. Our orbital diagram tells us to put 2 electrons into 1s. We'll do that as up and down, the same way that we did with helium. And then we've got 1 electron in our 2s. So we can put that with upspin or downspin. I don't think it matters. I put it in as upspin. Questions? When we've got multiple electrons, as it turns out, the subshells, the letters, within a principal shell, within a principal quantum number, don't have the same energy. And this is because of the electrons interacting with each other. So because of the way that the electrons interact with each other when they're in those different shapes, all of those different shapes you can think of as like being little magnets. It's like in the S, it's just one shape. It doesn't have any other shapes to interact with. So it's just what it is. In the P, so here we've got S, P, and D. In P, we've got all of these different shapes. Me doing a bad job of drawing in 3 dimensions. Classic. So in my mind, this red one's going left, right. This green one's going up, down. This blue one's coming out and going away, coming towards us and going away. All of those have a little bit of an electric force, a little bit of a magnetic force, and so they repel each other, and that makes it a little bit more stressful for them to exist. This is like having your own room, being the only one that lives in your house, in the case of the S subshell, versus being in the P, where you've got like 2 other families also living in the same house as you. There's a little bit more place for things to go weird, or there to be a little bit of tension. And D also has the same sort of a thing going on. The long and short of it is there's electron-electron interactions, and the subshells aren't going to have the same energy levels. This diagram, we've got energy as our axis, so energy going from lowest to highest, lower being lower energy, higher being higher energy. And we've got our different orbitals separated out here in terms of our S subshell, our P subshell, our D subshell, and that's just so that it's a little bit less confusing. So this is the order that we'll fill. We'll fill from the bottom up. So you'd fill up your 1s first, then your 2s, then your 2p, then your 3s, then your 3p, but then you skip to the 4s and go back to the 3d, then you do your 4p. So this is very fun for students to memorize, as you might imagine. Let's do an electron configuration and orbital diagram for carbon. and then break for the day. Carbon has how many electrons? Yes, it has 6 electrons. So carbon has 6 electrons. It has 6 electrons because it has 6 protons. Protons and electron numbers are even unless you have an ion. So carbon having 6 electrons, the first energy level that shows up, if we reference this diagram, 1s is the lowest, 2s will come next, 2p will come after that. So we'll use that for laying out our order. So 1s, how many electrons can we put in 1s? Still 2. So we've used 2 electrons, that means we have 4 electrons left. After 1s comes 2s. How many electrons can we put into 2s? 2. S can hold 2 electrons. So subtract another 2 electrons. We still have 2 electrons remaining. What comes after 2s? It's 2p. How many electrons can we put into 2p? For carbon, we can only put in 2 electrons because 2 electrons is all we have left. So we put in our last 2 electrons. We have 0 electrons left. That's our electron configuration. We would read it as 1s2, 2s2, 2p2. And we would draw our orbital diagram. We draw our 1s box. Our electron configuration tells us to put it up, down. 2 electrons in there. They have to be opposite spin. Our 2s is up next. Our electron configuration tells us 2 electrons. So up and down. And then we have 2p. How many of the dumbbells did we have in 2p? Who remembers? Anyone remember? 3. We had 3 dumbbells, 3 shapes. In 2p, each of those gets its own box. So 2p, we have 3 boxes because we had 3 dumbbells, 3 shapes. And our electron configuration tells us that we have 2 electrons left that we have to put into the 2p orbitals. And this is where our second named rule comes in, Hund's rule. Hund's rule says that when we're filling orbitals of equal energy, so if they have the same number and letter, then the electrons will fill in singly first with parallel, aka matching spin. So singly meaning they get their own boxes. And they're both up spin. That's the parallel part. So up and up for carbon. So what would not be allowed, for example, would be up and down. That's not allowed. And what is also not allowed would be up, then down, but in a different box. That is also not allowed. They would be in separate boxes. It doesn't have to be the first and the second. I just draw them in first and second. But in their own boxes and with matching spin, both pointing up or both pointing down. Questions about electron configurations or quantum mechanics? All right, we'll stop there for chapter 7 for today.